questions, comments, concerns, etc. before we get started today? All right. Small reminder before we begin, we are beginning lab schedule as normal. So starting this week, please do report at 1:30 to lab whatever day of the week your schedule tells you to, Monday, Tuesday, or Wednesday. The lab room is again 126. It's the last room on the right as you're headed towards that door that leads you to the bio building or out to the cafeteria. So lab room 126, start reporting as normal this week. This week's lab is, well, I guess we'll see when you get there. All right. Help turn that back on. Today is Monday the 22nd, and as I said on Friday, we are going over Newton's laws of motion. That's going to be our main focus for the next couple of weeks, talking about force and motion as a whole to build up our sort of conceptual foundations for the class, because most things in this branch of science have to do with either things moving or forces acting on them, most likely both. So, we looked over the laws. Let's very quickly glance at them again. First law says, and you do have to be able to identify these on the test, which is in about, the first test is in about a month and a half at this point. Closer to 1 month, not important. You have to identify these on a test. I will write out various statements, and you have to pick out of a lineup which one is first, second, and third, and number them accordingly. So you don't have to write them from memory, but you have to be able to identify and number them correctly. So you do have to know the numbers. So, to look at them again, briefly, first law says an object at rest stays at rest, and an object in motion, constant motion, will remain in constant motion unless acted upon by an outside force. This is the main thing we'll be focusing on today, and then in the coming days as well. Second law says net force equals mass times acceleration. Basically, if you have something and you want it to begin changing its motion, you have to exert an imbalance of net force upon it. The lump sum of the forces added together acting on that object have to not be zero. If the net force is zero, then the other side would be zero as well, and the object doesn't accelerate. Therefore, its motion doesn't change. And the third law says for every action force, there is an equal and opposite reaction force. We will be focusing on them each one at a time. So to start with, we're going to look at the first law. And to do that, there's a couple of definitions I want to go through to kind of lay the groundwork for the discussions we're going to have today. The first definition is inertia. When I was a kid, I was pretty much predestined to be a scientist because growing up I watched way too much Bill Nye, Magic School Bus, and Mythbusters. I'm bringing up Bill Nye because the theme song always said inertia is a property of matter, and it's stuck in my head, and it's true. Inertia is matter's innate tendency to resist changes in its motion. Inertia refers to matter's innate tendency to resist changes to its motion. The more mass something has, the more inertia it has. An object's inertia compels it to keep doing what it's already doing. For that reason, I'm going to tab back real quick to draw a comparison with something. For that reason, the first law of motion is commonly referred to as the law of inertia. If I was to give each law a name, it would be law of inertia, F equals ma, action, reaction. So the first law is called the law of inertia because that definition of inertia does refer to what's happening here. The first law says object at rest stays at rest, object in constant motion stays in constant motion unless acted upon by an outside force. At rest, remaining at rest, is doing what you're already doing. Constant motion, remaining at constant motion, is doing what you're already doing. Those objects, the matter involved here is resisting changes to its motion. They want their motion to remain the same, whatever their current motion is. And inertia is the measurement of that tendency to remain as you currently are, to not change your motion. The more matter something has, the bigger the mass measurement is, the more inertia the object has. Now, this whole slide is kind of nesting definitions, so I want to make sure to define mass for you as well. Mass refers to the amount of matter contained within something, the total amount of physical material, protons, neutrons, electrons, atoms, molecules, etc. For example, this water bottle is metal, water, and ice, and some air. I'd say this is probably about half a kilogram of mass, maybe 0.75 kilograms, possibly. And that measurement refers to the physical amount of material contained within my hand right now of all types, metal, water, and ice. And the more matter something has, you tend to think of matter as equating directly to the weight of the object, and on planet Earth that's not wrong. The more matter something has, the more it does weigh. But as it relates to these principles, the more matter something has, the more it wants to keep doing what it's doing, and the more it will resist your attempts to change that fact. To kind of demonstrate that, here I have two very different objects. This is water and metal, which is pretty dense, all things considered. Again, this weighs about half a kilogram. And this is hollow plastic. It's just an eraser. So a plastic shell filled with air. Not very dense, not a whole lot of matter right here. I'd call this like maybe 10 grams tops. And these two different objects will respond very differently to the same amount of force. What I'm going to do is now I'm going to flick each one. This object does not have a lot of mass, therefore it does not resist a change to its motion very strongly. I can pretty easily just flick that eraser. This, which has 20, 50 times as much mass, does not respond the same way. It has more mass, therefore it resists that change in its motion more than the eraser does. Does that make sense? Does that not make sense? All right. Now, mass is a variable that we can measure. And whenever I go over a variable or something we can measure, I want to make sure to go through the specifics of what we call it, how we measure it, etc. Mass, we measure it in units of kilograms in physics. Again, we like kilograms instead of normal grams because we tend to work with pretty big objects in physics. Again, chunks of metal, people, cars, planets, pretty big masses, compared to tiny piles of dust that chemists tend to work with. So physicists like kilograms for that reason. It's going to be the only unit that we want a prefix on. Most times if I give you a unit with a prefix like kilometers, you're going to want to turn it back into meters before you do any math to it in this class. This is the exception. If I give you a formula that has m in it, m being the variable that we've shortened mass to, for example, here's a formula with m in it. You want to make sure it's kilograms before you put that number in here. And we'll get plenty of practice for that. But anytime you see a lowercase m in a formula, it is asking you for the mass of said object. So variable m measured in kilograms. And mass is something that mathematicians refer to as a scalar. I will define that in a minute, I promise. Any questions about the definitions themselves thus far? All right. I will say that mass is the measurement of inertia. If you have measured mass, you have measured the inertia. Double the mass, double the inertia, double the tendency to resist changes in motion. So I guess another definition for mass would be the measurement of inertia. But there's one more vocab word I want to cover, and that's force, because that's the other word that's in Newton's first law. The actual definition of force is not all that complex. A force is a push or a pull. If you have ever exerted a force on something, it's either been pushing it away from you or pulling it towards you. And that's true of all forces, whatever type they are. Even, deep space cosmic levels of gravity, it's still just a pull. A push or a pull that can cause an object, which is a keyword for mass. A push or a pull that can cause mass to accelerate. And that's all a force is. You're either pushing something, trying to move it away from you, or pulling something, trying to make it move towards you. The definitions don't all have to be very complex. So, push or pull. And in physics, we like to measure force in units of newtons as opposed to pounds. When you weigh yourself in pounds, that is the force of gravity. So pounds is a measure of force. It's just not the metric measure of force. We're going to stick to newtons for this class. But just for context, 1 pound is equal to about 4.5 newtons. So if you ever wanted to know how much you weigh in newtons, you take your weight in pounds and multiply it by 4.45. Again, just for scale, I weigh about 1,000 newtons. So, we measure force in newtons instead of pounds. The variable for force is going to be uppercase F in any formulas that require it. And as opposed to mass, which is a scalar, a force is something that we call a vector. So now I get to define those two vocab words. It's a very vocab-focused day, unfortunately. But any questions before I switch slides? All right. So, the difference between scalars and vectors. Vector is just a fancy word for a measurement that can have a direction. If something has a direction, if something you can measure points in a direction, we call that a vector. I am at this point contractually obligated to bring up the villain of Despicable Me 1, Vector. Because he called himself that because he, quote, commits crimes with both magnitude and direction. That was the exact quote from the movie. And that's exactly what a vector is. It's something that has a magnitude, which is just a number. Magnitude is just the measurement. So if something weighs 10 newtons, the magnitude of that measurement is 10 newtons. A vector has both a magnitude and a direction, because every single force has to point somewhere, right? A force is a push or a pull. I got that backwards. Push or pull. It has to point somewhere. You cannot have a directionless force, right? You can't force something in a direction if there's no direction. All forces have directions inherently, and that makes all forces vectors. And in physics, if something is a vector, if something can have that direction, we want to know what it is, because it's going to be important. That direction is data. We need data, because data is, again, the thing that we measure to try to get as close to the truth as we can. And since that's part of the data, we need it. We have to take it into account. For example, if you wanted to figure out, how quickly something would move east, wow, I get turned around between my directions and yours. If you want to figure out how long it takes something to go east, but all the forces acting on it push west, you need to know that, right? Because if all the forces point west, it's not actually going to go east, and then you got to fix what's going wrong. So if something can have a direction, we want to know it. The direction is going to be important. And if something is a vector, I will always tell you that it's a vector, and I'll tell you what the direction, why the direction is going to be important, and how we're going to utilize it. This right here is a list of common vectors in physics. Force is, I'd say, the biggest one, because again, you can't have a force without a direction. Every push or pull points somewhere. But some other common vectors include displacement, velocity, and acceleration, because if you are moving, you're moving in a direction. You cannot have directionless motion, right? You have to be headed north, south, east, west, or some combination of the above. Acceleration is a vector too, because if your motion is changing, it's changing in a direction. You're either speeding up forwards or slowing down backwards. Those are directions. And force is a vector. That means also every variation of force is also a vector. That does include weight. The direction for weight is down. It's a force that points down. and we'll define momentum in a few weeks. Now, these vectors are in contrast to scalars, which is what I said mass was. Mass is a scalar, and scalar means that it doesn't have a direction. Scalars are just numbers. See right here. If something doesn't or can't have a direction, we call that a scalar. Scalars are only a magnitude. A magnitude is just a number. You can't have 3 kilograms up. You can have 3 kilograms, and you can push it upwards, but the force points up, the mass doesn't. Mass cannot have a direction. There's a few things that just can't have directions. Those are scalars. We don't care about the direction because it doesn't exist. So I'll always point out whether or not something has a direction or doesn't. If it has a direction, we need to know it. If it doesn't, then you're fine. So mass is one of the things that just can't have a direction. Neither can temperature, neither can energy, neither can time, actually. You might think that time's directions are forwards and backwards, but we don't really have, like time doesn't flow backwards. Time only really flows forwards. So there's no direction other than that. We consider time to be a scalar. So, again, wherever this becomes relevant, any type of unit I bring up, I will tell you if it's a vector or not, if it has a direction that you should care about. So, to tab back briefly, force is a vector. We care about the direction things are getting pushed in. Mass is not a vector, so there's no direction arrow to worry about here. But if something is a vector, we care about direction. We're commonly going to draw them with arrows, or we're doing like creating pictures to help inform our math and inform our concepts. So I think I actually ran out of things to say. Any questions so far? All right. Now, that was a lot of definitions. Let's start applying them. Let's actually start using this information. Behold an object at rest. This is a pretty big boulder. Those are trees in the background, so I'd say a human would come up to about here, maybe here. So, pretty big rock. This object has a lot of mass. Therefore, it has a lot of inertia. Therefore, it does not want to change its motion. From experience, are boulders hard to get moving? Yes, a lot of mass. You with your human muscles likely cannot very easily get this thing to start moving. It takes a lot of effort to make it move because it has more mass. Now, the counterpoint to this is, because Newton's law, the first law of motion says an object at rest stays at rest, and an object in motion stays in motion. This object, same boulder but rolling. Let's just say it's an Indiana Jones movie. This object is also engaged in constant motion. Technically not moving at all is constant motion, and rolling at constant speed, constant direction down a hill is also constant motion. Therefore, this boulder's inertia is telling it, keep doing that until Indy's a pancake, until something stops the boulder. And it's not going to be me. I can't stop that thing. So technically, in terms of the inertia, in terms of the equilibrium, these two situations are the same. As long as the boulder's motion is constant in both, as long as velocity equals 0 and it stays at 0, or in this case, as long as velocity always equals like 10 meters per second this way, those are both forms of constant motion. And in both cases, the boulder's inertia says, keep doing the thing you're already doing. Stay still if you're still. Keep rolling at Indy if you're already rolling at Indy. So those are both equilibrium states. So it's actually time for the vocab word, unfortunately. Matter is lazy, or rather, it doesn't like change. You have to force it to change. And if it's currently not changing, if its motion is constant, either constantly 0 or constantly something else, it's in an equilibrium state, and its inertia will keep telling it to do what it's already doing. Equilibrium can be kind of dynamic, it can be kind of complex. Rolling down a hill at constant speed is an equilibrium state. An equilibrium, I forgot I had another definition slide. Equilibrium is the state where all the forces acting on something add up to zero. If an object's in equilibrium, it'll keep doing what it's already doing. Equilibrium is the state where every force present adds up to zero. Equilibrium is surprisingly not the state where there are no forces acting on an object. It's the state where every force cancels out. There is no net force pointing in a direction compelling the object's motion to change in that direction. So, after all that vocab, any questions first before I do anything else? All this information sound familiar? Yes.
Are you gonna put the PowerPoint in white space?
Sorry?
Are you gonna put the PowerPoint into white space?
It should already be there. Let me both show where that should be and also check. Also, Brightspace isn't logging in for me for some reason. There we go. It should be there. If it's not, I will very quickly fix that.
We have our chapter 1, but not our chapter 2. Just check it.
Oh, that's my mistake then. I am very sorry. Okay, yeah, I see. That's my fault. Where did those go? All right. Thank you so much for bringing that to my attention. They should be there and be visible now. Sorry about that. Anything else before we start applying all of this information? Okay, so. Come on. Now let's look back at that boulder. This rock is at rest. This implies that the boulder must be in a current state of equilibrium. I've done a lot of I work enough with computers that I tend to start thinking and coding if-then statements. So here are some if-then statements. If an object is at rest, it must currently be in a state of equilibrium. If an object is in a state of equilibrium, then the net force acting on it must be zero. Net force being zero means that all the forces present have added up to zero. Note again, sigma F, net force. This is the sum of every force present. And for equilibrium to exist, those forces must all be canceling out. Because there's actually no such thing as there being no forces on an object. Every object in the universe has some amount of force acting on it. You cannot escape it. For example, looking at this rock, what are the forces currently acting on this rock that you can identify? Gravity, very good. You can't really escape that living on planet Earth. Markers are dying. How many pulls till I find a marker that works? There we go. What I'm about to draw is called a free body diagram. That's just a fancy way of saying I'm drawing a box and I'm going to put arrows on it representing all the forces that are on the rock. So this is just the science way of saying I'm drawing arrows to show the forces and how they interact. And you've mentioned that this boulder must have some force of gravity pulling it down. That's going to be true of every single object on planet Earth. Frankly, you don't even need to be on planet Earth for gravity to happen. You just have to be in the same universe as planet Earth. Because even if you're in the Andromeda galaxy, technically, Earth's gravity didn't go away. It just shrank. There's a gravitational pull between you and Pluto right now, which is too weak to do anything about. But it exists. You can never escape gravity, and since Earth is the closest thing to us, Earth's gravity is the thing that we feel most, and it pulls us towards the core of the Earth, which will always be straight down. So, Earth's gravity, which I'm abbreviating here as F subscript G, there's lots of different types of force, so I'll differentiate them by putting a subscript on the F to try to demonstrate, to try to note what force I'm talking about. So Fg is force of gravity, and I'll add more subscripts as we talk about more types of force. So here, force of gravity pointing down. Now, is that the only force acting on this rock? No. If that was the only force acting on this rock, the rock would be falling. If this was the only force, this would be the net force, and the boulder would be in a state of free fall. That's not currently happening. So what else must be happening here?
A force from the ground?
The ground. The ground is going to push up on the rock. I'm going to call that Fn. I'll explain why in a minute. This scenario, the boulder sitting on the earth, the ground is literally supporting the boulder and preventing the boulder from falling through the physical ground. This is true of anything that is sitting on a surface. It's true of a golf ball of science sitting on my desk. It's true of you guys sitting in your chairs. There are at least these two forces acting on this boulder. These are the two biggest ones. And again, the boulder's equilibrium is not defined as no force. It's defined as these two forces canceling out. One pointing down, one pointing up. They both add up to 0. When you calculate net force, they add up to 0. And a net force of 0 creates the equilibrium state, allowing the boulder to remain in place. So, different version of the free body diagram. We got two different arrows representing those two forces. Force of gravity down, normal force up. I'm calling it normal force, largely out of habit. And when I say normal for this type of force, this is the supportive force that the ground is exerting up on the rock. And it's the same force that your chair is exerting up on you now to keep you in the chair instead of falling through the chair. I call it normal force not because it is common or typical. It's not that definition of normal. It's the mathematician definition of normal. If you haven't had a geometry class in a minute, first of all, that's okay. Second of all, to a mathematician, normal is a synonym for perpendicular, weirdly. And that's because the force the ground is exerting upwards is perpendicular to the level of the ground. If the ground is horizontal, it's going to push upwards on the rock, perpendicularly out of itself. And that is a direct response to the rock pushing down into the earth. Secretly, this is because of Newton's third law. Action, reaction. Push into earth, earth pushes back up on you. All laws are connected, as you're going to find out in these weeks. So that's why I call it normal force. Perpendicular math normal. I want to make sure that was established here at the beginning. It could also be called supportive force or just support force. The textbook itself even uses that term for it occasionally, which is a totally fine way of saying it. I just use normal force and Fn out of habit. But very quickly, I do want to prove that it is always perpendicular, even if the object in question isn't flat ground, because vertical walls do this too. Since the walls are vertical, perpendicular out of the wall would actually be horizontally. And this is what happens when you lean on a wall. I push horizontally into the vertical surface, it pushes horizontally back out. So all surfaces do this, and I call it normal force because again, it's perpendicular to the surface. But it is fairly typical, common, normal, if you want to think of it that way. Now in this scenario, we've identified these two forces. So let's use them, and all the definitions so far, to do a teeny tiny amount of math. This boulder weighs 5,000 newtons. That's about 5 of me. It is currently sitting at rest on the ground. So, here's the prompt. Here's the initial statement of the question so you get all your data. Boulder's at rest. At rest means current velocity, current speed is 0. It's not moving at all. It weighs 5,000 newtons. Using that information, first question, is this boulder in equilibrium? Yes. How do we know this?
It's at rest.
It's at rest. If an object is at rest, it must be in equilibrium. Rest state is constant motion of 0. Motion is constant, you are by definition in equilibrium. So yes, this boulder is in equilibrium. First question accomplished. Second question, what is the net force acting on this boulder, given the previous question? 0, very good. We've established we're in equilibrium. If you're in equilibrium, net force must be 0. This again does not mean that there are no forces on the boulder, just that all the forces present are canceling out. So with that information, last question, what must the magnitude and direction of the supporting normal force acting on this boulder be? I'm going to show you how to think about this one. I'm going to kind of treat it like a math proof. We've determined these are the two forces that are present. We've also determined, because the boulder must be in equilibrium as described, net force on the boulder must currently equal 0. Like, we know this is a fact, we established it in the earlier parts. Net force must equal 0. But the thing is, there's another definition for net force. We know net force is 0, but actually the definition of net force is all of these present forces added together. So there's not really a more specific formula than that. If I ask you for the net force on an object, you just take every force that's present, you add them up. In this case, then, I can take this fact that we've already determined, and I can add an extra piece onto it. Because we know, not only is net force 0, net force by definition must be this plus this. The force of gravity on the boulder plus the normal force on the boulder. Those are the two forces that are here. They must add up to 0 for the boulder to be in equilibrium. This is true of every equilibrium state. Every present force must add up to 0. And the thing is, that means that we can now treat this as 0 equals gravity plus normal force. We want to determine what that normal force is, and we already know what the gravity is. I told you how much the boulder weighs, 5,000 newtons. So we can just plug that number in there and kind of do a little bit of algebra to figure out what normal force is. So I'll just rewrite this one line down. 0 equals, we're going to plug in a value for gravity, and since force is a vector, you have to be very specific about your directions. Now, since we like math in this class, we're going to treat our directions the same way that geometry people do, where positive y is up and negative y is down. Therefore, if gravity points down, we're going to treat it as a negative number. So I'm going to write in negative 5,000 for FG, and I'll leave Fn as unknown. Does that feel all right? Since force is a vector, we really need to care about direction. We need to be specific and treat it the same way geometry people do their graphs. So now we just solve for Fn, and you know, we went over algebra last week. How do we get there?
Add 5,000.
Yeah, we're gonna add 5,000 to both sides. So that's gonna give us positive 5,000 newtons equals that normal force. And if negative meant down, positive means up. So the normal force on this boulder must be, in this scenario, 5,000 newtons upward. The ground is perfectly counteracting the force of gravity in order to keep that boulder from just crunching through the crust of the planet. If the ground can't create that much force, the ground gives way and the boulder sinks. Yes, sorry.
What is FG?
Force of gravity. Boulder weighs 5,000 newtons. Weight means gravitational force. So I will write that usually as FG in my order. Does that make sense? Now, if an object is usually just sitting still on the surface, this relationship will usually be true. If the only two vertical forces present are gravity down and normal force up, and the object is in equilibrium, usually they'll just cancel out perfectly. It's technically not a guarantee. We'll look at some weird scenarios further down the line, but it's usually a pretty safe assumption if you're just sitting on a surface. Again, this scenario is pretty much true of you your whole life as well, as long as you're standing or sitting on something. There's always some force holding you up, keeping you from falling into the molten core of the planet. Which is nice. I don't want to go there. Questions thus far? All right. Got a couple more examples real quick. Let's look at a different object, a different free body diagram. Here we have a different box with 4 different forces acting on it rather than just 2. 4 different forces, 100 newtons up, 250 newtons to the right, 125 newtons down, 200 newtons to the left. And we have to figure out what the net force acting on this object is, and from that determine if it is in equilibrium or not. Now, the definition of net force is add all the forces together. However, given that forces are vectors and that all these are pointing in different directions, do you feel like you want to add 100 to 250 to 125 to 200 directly? No. If I put this on your test and you gave me a final answer of 350, 550, 675, I would be sad. And that is because all these forces point in opposing directions from each other. If they were all pointing in the same direction, that would be teamwork. They'd all be pulling in one unified direction. They would all add up normally in that case. But here they are all opposing each other, like how gravity and normal force were opposing each other on the boulder. And when forces oppose each other, they work against each other. One of them is positive, one of them is negative, and therefore, when they add together, the answer is actually smaller. So we have to factor in the direction of each of these vectors. But we also have to factor in axis, because you can't actually add right to up. You probably dealt with this before in a math class, but if it's been a second, x can only be added to x and y can only be added to y. And when I mean x and y, the x plane is horizontal and the y plane is vertical. The reason for this is, if I'm jumping up and down, how far side to side am I moving? 0. What happens in one axis does not immediately affect the other axis. Upward forces will never by themselves cause side to side movement. And so that means not only do we have to factor in direction, but also axis. Now we've already got a free body diagram here, so I'm going to erase the boulder diagram and instead do some math over here. these four forces are really acting in, we can consider them to be two different pairs of forces. We've got the pair that's opposing vertically and the pair that's opposing horizontally. And so the way that I'm going to show this mathematical proof, I keep misplacing the marker that has the most ink in it. I am going to do net force addition twice, once for the x-axis components and once for the y-axis components. We're not going to do a lot of 2D, two-dimensional work for this particular course. It'll come up occasionally, and I'll always be very specific about x versus y when it happens. Just want to make it clear in this example that the axes do matter when it comes up. So, first off, since we can only add x to x and y to y, let's look at the net force in the x-axis separately from the net force in the y-axis. So in the x, we've got 250 to the right and 200 to the left. Those oppose one another, so one of them has to be negative to demonstrate that fact. And typically, again, if you've graphed anything recently, typically mathematicians say right pointing x is positive and left pointing x is negative. I'm going to continue that trend for the most part for this particular class. So I'm going to call the right pointing arrow positive 250 and the left pointing arrow negative 200 for this reason. Technically you can reverse that if you wanted to, as long as one of them is negative because they oppose each other. So net force x-axis, I'm going to take both x numbers, add them together. But technically, one of them is negative because they oppose each other. And as a result, the net force in the x-axis is 50 newtons to the right. Since I plugged in a positive number for the right pointing one, the positive answer means rightward pointing. And we can do the same thing the y-axis. 100 newtons up, 125 newtons down. Again, they oppose each other, but they usually indicate upward as the positive of the two. So I will write those as positive 100 plus negative 125, which is just minus 125. And that's going to give us a net force in the y-axis of negative 25 newtons downward. The negative here matching the direction of the down pointing vector. So the net force in the y-axis is downward pointing. So to actually get back to the original question, is this box in equilibrium? No. All the forces here do not add up to zero. This box is not in equilibrium. Its motion is about to change. Specifically, since the net forces are very right and a little bit down, it's probably going to start heading in this direction, east-southeast. So, main takeaways from this one, the axis is important. It's not going to come up all the time. We're going to do mostly one-dimensional motion, but it'll come up occasionally. Forces are vectors. We care not only about direction, but also axis. And this is also a demonstration of a non-equilibrium state. Questions on this one? Okay. I got one more, and we'll just kind of set this one up, so if we don't conclude it for today, we can use it as the springboard for Wednesday. Let's look at a different object entirely. Here we have a car that is going to be driving. Let's say it's the interstate, you've got cruise control on. Let's say 70 miles per hour for legal speed limit reasons. This SUV is driving at constant velocity, and it currently weighs 10,000 newtons. That is the information given. Based on that information and what we know about physics, is this car in equilibrium? It is in equilibrium, because equilibrium, net force of 0, just creates constant motion, not necessarily no motion. Equilibrium causes constant motion, and that can include constant velocity. So don't erase the previous if-then statement in your notes. I'm just going to give you a second if-then statement. If at rest, then equilibrium, but also additional statement, if constant velocity, then you are also in equilibrium. And still, if equilibrium, net force equals 0. So this car, as long as the velocity is constant, is still in equilibrium. That means that every force on this car still adds up to 0 even though it's moving. A moving object can still be in equilibrium as long as its motion is totally constant. That's the exact function of the cruise control switch in your car. So that's the first takeaway from this example. Equilibrium does not mean motionless, it just means motion is constant. That can include constantly at rest or constantly moving at some constant velocity, same speed, same direction. Does that sound all right? Okay. We can real quick do the force body diagram just to identify these forces, and then we'll pick up from there next time. Assuming this is on planet Earth, the same two forces from the boulder would still apply. Earth's gravity still pulls down, and the road exerts a force upward to keep the car from literally crashing through the pavement. But hypothesize with me real quick, what other forces could be present on this thing?
Air resistance.
Air resistance. I'm going to lump in pretty much every form of friction in this particular arrow and just write FF for force of friction. That can include air resistance, that can include friction from the road on your tires. That can frankly include the friction inside of the engine, because if there's moving parts, there's friction. You can't avoid it. It's the bane of all mechanical engineers. Now, if a car is in equilibrium, every force present must add up to 0. The normal force and the gravity can still add up to 0 and cancel each other out as per normal, as with the boulder. However, if these were the only forces present, that means there's nothing here canceling out friction. So there has to be something else driving the car forward just enough to mitigate the friction that's naturally slowing it down. And that would be, again, the function of cruise control, or if you're just barely tapping the gas to maintain constant speed. If you have cruise control on, or you are actively pressing the pedal down yourself to maintain your speed, to keep your speed from dropping naturally, that is the tiniest amount of force forward to add up to 0 with the friction backward. So this is what I would say dynamic equilibrium looks like. The boulder's static equilibrium. It's not moving. This is dynamic equilibrium. We have motion, there's more forces, but they still add up to 0. And we'll start talking about some math for this and define friction and such next time, as we also start looking at all of the math for motion itself. Questions? All right, let me know if you need anything. Do again come to lab as per normal. You should also begin looking over that first homework batch that is on, I guess there's 2 homework batches. Homework isn't due, it's just practice that you should be able to do by the test.
Is there anything specific we need to bring to them?
Just a calculator and team spirit. And if you need anything, have a wonderful day. Stay warm, please.
Have a good day.
Oh no.
$150 less.
I know.